Well, we want to begin discussing inverse trigonometric functions, and this is certainly related to the idea of inverse functions that we had earlier in the semester when we were talking about algebra. So let's kind of remember the idea that we ran into there, that the only types of functions that had inverses were functions that were one-to-one, and the test for being one-to-one was called the horizontal line test. And the issue with one-to-one is that we can't ever have a y used more than one time. To have a function, we can't have an x used more than one time, one single value of x. And to have a one-to-one function, not only does it have to be a function where only a single x can only be used one time, but for one-to-one, a single y can only be used one time. And that's tested with the horizontal line test. So if we think about drawing a horizontal line, if it crosses, one horizontal line goes with one y value. And if that one y value or that horizontal line crosses the graph more than once, every place it crosses it, there's an x that goes with that y. So because of the nature of the sine function we see here, then it fails the horizontal line test miserably. Almost all of the appropriate horizontal lines cross the graph in an infinite number of places. So as it stands, this function does not have an inverse. Now, if we restrict, in fact, let's look at this graph. Okay, this is a little better graph than what I have above. So in this graph, it's the same graph except a little more precise. And I've got the dashed lines, but notice where these red dashed lines are, if I look at only this part of the graph, so if I look at the part of the graph before it turns back down or before it turns back up, then that part of the graph would in fact satisfy or pass the horizontal line test. And so we talk about restricting the domain of the sine function to only be using values of x between negative pi over 2 and positive pi over 2. And if we look at that restricted function, that restricted domain function, then that function will in fact have an inverse. Whoops, what happened there? Went crazy. So from this new function, okay, so we're taking the sine function but restricting its domain between negative pi over 2 and positive pi over 2, but notice its range takes on the full values of y that the sine function takes. The sine function goes between negative 1 and 1, and if we use only this part of the function, we still have all the appropriate y values, and that's an important part of this. We want it to include all the y values we could have, but still make it a one-to-one function so that it has an inverse. So our new function, and not really a new function, but the one we're going to use to create an inverse from, has these characteristics. You see it, the domain between negative pi over 2 and positive pi over 2, and the range between negative 1 and positive 1. Well, as we were just mentioning, the sine function with those restrictions has an inverse, and we call it y equal, and that looks like an exponent of negative 1, but it's much like the function notation, the inverse function notation we used when we were calling our functions by the name of f. So that's not an exponent of negative 1, it indicates the inverse sine function. Now in some books, this is actually called the arcsine function, okay? So inverse sine that we see like this and arcsine mean the same thing. If you're ever in that position, you'll be able to translate what is being told to you. Now let's, by the way here, what I've done in this case is I've taken the sine function with the restriction of the domain between negative pi over 2 for x and a positive pi over 2 for x, and I've just calculated the appropriate y values for each of those. And you see I took negative pi over 2 and negative pi over 3 and negative pi over 4 and so on, and I calculated the appropriate y values. So this is the sine function. And of course, These are domain values on the left, the x's, and the y's are the range values of this sine function with the restrictions. Now, remember when we dealt with functions in algebra and their inverses, we remember that the result of the inverse was changing the positions of x and y. So you see here, if our x is -1, then our y is -π/2, which is just the opposite of this. So in the sine function, we put in angle values and we get out real number values. In the inverse sine function, we put in real number values and we get out angle values. And that's the thing to remember. When we take the inverse sine of some number, we get an angle. That's the result of taking the inverse sine. So you see the relationship. This is just the same kind of relationship we had before. So if in this case, for instance, whoops, hold on, let me see here if I can, I apologize, it seems as, well, I've got all kinds of problems here. There we go. If we look at the inverse sine of -1, we look over here, oh, inverse sine of -1 is going to be a -π/2. And see, that's what that is this -π/2 is the angle that we take the sine of to get -1. So when we say inverse sine of -1, we say, oh, we're looking for an angle. And when we take the sine of that angle, we have to get the result -1. That's kind of this relationship here. So I've stated this in a bit of a different way, that when we look at the function y = inverse sine of x, the domain are numbers. The domain is what the range was over here. So it's their numbers between -1 and 1. And the range, the output, are going to be angles between -π/2 and +π/2. That's an important idea. We'll look on the next page at an appropriate graph. Okay, so from the previous page, this is the function that we're taking the inverse sine of. Okay, that is this part of it, and the inverse sine function then, just as an example. Notice the point -π/2, -1 is on the graph of this restricted sine function, and so -1, -π/2, see, -1, -π/2 is on the graph of the inverse sine function. And for instance, if we came over here to -4, -π/4, then our sine value, our y value, would be what? -√2/2. Well, notice here, when we go to where -√2/2 is, whoops, about right here, then our y value is -π/4, which would be about right here. So we're basically taking these points and plotting them, taking their inverses, and then plotting those inverses, and this is what we get. So this is the graph of the inverse sine function, which we probably don't use a whole lot right away, but when you get to calculus, it's important to know what this graph looks like and some other inverse trig function graphs look like. Notice, though, in the inverse trig function, we take the inverse sine function, we put numbers, the domain, we put numbers between -1 and +1 in as our x values, and what we get out are angles between -π/2 and π/2. Those are our y values. So the result are angles, as I mentioned previously. Quite frankly, this what we're doing now, this introduction, is a little bit difficult to comprehend. I recognize that. And it takes doing some problems that we do later on, and actually that's a second second lecture. But we've got to know the big picture before we can work on problems. So the definition of the inverse sine function goes this way. The function y equal inverse sine of x, this is true if and only if we take the sine of y, see, we take the sine of y and we get this result x. That's what this says. Y equal inverse sine of x if and only if x is equal to the sine of y. In other words, we see this, we take the sine of this value, then we get this value. Now, the requirement is, though, remember, the domain of this inverse sine function, the x's are between -1 and 1. So that's what goes in here. And the result we get, the y's, the result of finding an inverse sine, are angles between -π/2 and +π/2. And when we're actually working on problems, as I've been mentioning it, it's convenient to think of the value of the inverse trig function as an angle. In other words, the result, the y, the value of inverse sine, we think of it as an angle. So back to, if we see y is equal to inverse sine of 1/2, then y is the angle that falls in the interval between -π/2 and +π/2, whose sine is 1/2. And so that means that inverse sine of 1/2 is going to be π/6, because the sine of π/6 is 1/2, and π/6 falls in this interval. Like I said, it takes a little bit to get our head wrapped around. Until we actually do problems, we don't see quite how it all fits together. So let's look at an example. Find the exact value of inverse sine of 1. So here's how I'm thinking about this. Inverse sine of 1 is an angle. And it's an angle that has to be between -π/2 and +π/2. So over here, I put in red that angle has to be between this -π/2 and this +π/2. So we can have negative angles, we can have some positive angles, but we can't have angles that are over here in the third or fourth quadrant, and we can't have an angle that goes clear around and back into this quadrant. So anyway, our angle is between -π/2 and +π/2, and furthermore, the sine of the sine of theta has to be equal to 1. That's what we were showing above, see? The sine of y, see, the sine of y has to be equal to x. Well, here it's the sine of theta has to be equal to 1. So the sine of what angle is 1? Well, one angle we know is π/2. The sine of π/2 is 1, and since π/2 falls in this interval, okay, between -π/2 and π/2, then that angle, that theta, that π/2, qualifies to be the correct theta. So our conclusion is the inverse sine of 1 is the angle π/2. Oh, let's look at a different one now. Find the exact value, and by the way, exact value, and you'll hear me say this more than once. When we see the key exact value, that means we do this without the aid of a calculator. That's really that's the key, that's what it's telling us. So find the exact value of inverse sine of -√2/2. So once again, I'm thinking of inverse sine result as being an angle, and I'm calling that angle theta. Now, here's what we know about that angle theta. It has to be between -π/2 and π/2, and also the sine of that angle theta has to be this -√2/2. So we begin searching, okay? Sine of what angle is -√2/2? Oh, the sine of -π/4 sits that. So if we come to here, the sine of -π/4 will be -√2/2. And -π/4 is between these two angles. So then that tells us, oh, well, we know theta is -π/4 then. So that is the inverse sine of -√2/2 is the angle -π/4. Now, here's where some confusion can appear. So let me make this clear. If we start here and see this blue line and we go clear around to this position, that's 7 pi over 4. And the sine of 7 pi over 4 is negative square root of 2 over 2. So why didn't we choose our theta? Why didn't we choose our theta to be 7 pi over 4? Well, that's because 7 pi over 4 is beyond pi over 2, isn't it? See, 7 pi over 4, we have to go clear out of the interval. It gets bigger than pi over 2. And so that's the reason we rule it out. We had to go in a negative direction so that we didn't leave that interval. Well, let's turn our attention to two particular other inverse trig functions, and that's the inverse cosine function and the inverse tangent function. And you notice the notation there. Sometimes the inverse cosine function is called arc cosine, and sometimes the inverse tangent function is called arc tangent, A-R-C, arc tangent, arc T-A-N. And first we're going to look at the inverse cosine function. So as again, if we look at the cosine function itself, say, and of course it extends forever in each direction, it would fail the horizontal line test as well, just like the sine function did. So what we try to do here is capture a part of the function that has a full range of y values all the way from -1 to 1, but never turns around. And you can see that if we restrict this function from 0 to pi, then we'll have such a situation. So this passes the horizontal line test now. So this is just basically a statement of what I've already said there. Okay, just if we look at this restriction from from 0 to pi, then we have something that we can find an inverse of. And the inverse would look like this. And just as an example, to give you an idea, for instance, remember how the points are reversed. So normally on this restricted function, the point 0, 1 is on the graph, so that would be a 1, 0 here, and we see that. And we kind of look at the end. Well, a pi -1 will be on the graph, so that means a -1 pi will be on this graph. And so what was the domain here ends up being the range here. And what was the range here between -1 and 1 ends up being the domain here. So for instance, the point pi over 2, 0 is on this graph, so 0 pi over 2 is on this graph. And we see this is what this graph would look like. The inverse of this function looks like. Well, here's the definition, and this is much like the definition we saw for inverse sine. Y is equal to inverse cosine of x if and only if x is equal to the cosine of y, which means if we have this scenario, it means y is an angle. And when we take the cosine of y, we get this value x. And the inputs into the inverse cosine function, that means the domain, are values between -1 and 1. And the outputs of the inverse cosine function, that means the y's, are angles between 0 and pi. And so if I looked at that on the unit circle, that would be angles that fall in this red area, right? First and second quadrant, but they can't go negative or they can't go around more than once to get in there. They have to only be less than 1 revolution there. Well, now a quick look at the inverse tangent function. So here I've sketched in a graph of several cycles of the tangent function. Okay, of course, these cycles repeat forever left and forever right. And so, of course, as we see this graph, it fails once again the horizontal line test miserably, because any horizontal line will cross the graph an infinite number of times. But you see, I've kind of focused in on this one particular cycle, this blue cycle. So what we're going to do here is we're going to think of the idea of not looking at the entire y equal tangent x function, but only the part of the function that lies between negative pi over 2 and positive pi over 2. That one cycle is all that we're concerned about when we're dealing with the inverse tangent. So this restricted tangent function has an inverse. Okay, and what does that inverse look like? I guess I'm a little ahead of myself. Let's not worry about what it looks like yet. Let's look at the definition, which follows the same scenario that we've been following. Y equal inverse tangent of x if and only if x is equal to the tangent of y, meaning if we have y as this, then when we take the tangent of y, we get this result x. Now here, because what we've seen before, remember the x's, well, because what we've seen before here, the result of a tangent, these x's are all real numbers, and our outputs, see, we have a reversal of roles of the domains and ranges, and so the outputs of this inverse tangent function are y values between negative pi over 2 and positive pi over 2, but they can never be negative pi over 2 because the tangent function is not defined there, or positive pi over 2. I didn't say that quite as neatly as I wanted to. Well, because of this definition, this is what that function looks like. See, if we take this and reverse the roles of our x's and y's, so just as an example, 0, 0 is on this graph, pi over 4, comma 1 is on this graph, and negative pi over 4, comma negative 1 is on this graph. So that would mean if we have an x of 1, our y value would be pi over 4. See, we switch them. If our x is negative 1, then our y value will be negative pi over 4. And you see how those vertical asymptotes here end up being in the inverse tangent function horizontal asymptotes. So this is an important graph when we get into calculus. This is an important graph. But we're a long ways from calculus right now. So remember that the output of this, the y's, never get as high as pi over 2 or never get as low as negative pi over 2 because we have this restriction in these asymptotes. So in this case, the output looks kind of like the inverse sine output, except we can't have it being negative pi over 2 or positive pi over 2. The output will never be one of those values, but it's in between, as opposed to what we see when we look at the inverse sine output. Well, I hope this has made some sense. I mean, like I said earlier, I know it's hard to grasp and digest all of that I've told you, but what's going to be important later is how we apply this information. And in the next video, which is inverse trig functions problems, then you'll see how we approach the problem and how we use these definitions to our advantage. And I think it will be easier then. So signing off from this introduction.